So we are glad to have Arnaud Brothier today from UNSW Sydney. He will talk about forest groups.
All right. Thank you very much, Sébastien, for the introduction. And thank you, Sébastien, for inviting me to give a talk. It's the first time I'm going to discuss about this new paper that I just put on archive about 10 days ago. And I think that's probably the paper I worked the most in my life on, because I worked about 2 years on it. And you will decide if it is interesting or not. Yeah, so it's a bit of a mix of subfactors, conformal field theory, and some group theory. So we'll see what it goes here. Okay, so I'm calling this forest groups. And so what my plan for the talk is, first, I want to recall everything comes from a great idea of Vaughan Jones. And I want to put like one slide to put like the big picture, if you want, like the big idea. And explain what are the mathematical objects involved that come from different parts of mathematics. And then I will basically propose a program in that vein. Okay. I will see some applications that are today in group theory. All right. So there's a lot of things to do. And I've chosen to do some group theory right now. So you see some application in that. And I will give a lot of possible direction. Okay. So if you have nothing to do and there's like one additional direction you want to focus on, I'm going to give some. All right. Okay, so let's start. So the first slide is the dream of Vaughan Jones. And maybe I'm going to unlock the zoom. So it's quite a big picture here. So it comes from the fundamental question of Jones. So Jones, I should have put it actually, initiated the modern theory of subfactors in 1983. This famous paper, Index for Subfactors. What are subfactors? They are inclusion of fundamental algebras, as you can see. So they come from functional analysis. Okay. So these beasts are algebras that have nice analytical properties. Okay. And the theory, the factor in itself, so a single algebra, you don't really care in the theory of Jones, or not so much actually. What is really rich is to look at an inclusion, because the inclusion captures an extremely beautiful mathematical structure. It is more algebraic. Okay. And this structure can encode a lot of groups, but also quantum groups. I'm not going to define precisely which quantum group I'm talking about, but this is really included in that. Yeah. And moreover, even more mysteriously, there are like some exotic subfactors. Okay. So that really produce some amazing tensor categories. And in fact, this reminds me of a quote that Ettinghoff gave at one of the subfactors conference in Vanderbilt. That's probably Zhengwei will remember, is that Ettinghoff say, like they build this wonderful theory of fusion categories, and he say, you guys are the only person who actually give us give us like fundamental example in these fusion categories. And it is true, it kind of show like the richness of subfactors that come from functional analysis. Operator algebra will give you beautiful algebraic objects. Okay. All right, so that's the left-hand side and the theory of Jones, that is a beautiful field in mathematics. But fundamental algebra, as you may know, have been introduced about almost 100 years ago to describe quantum mechanics. Okay, so from the very beginning, it's linked to physics. And the right box, as you can see, is CFT. So by CFT, I mean conformal field theory. So it's a quantum field theory with some conformal group invariance. Okay. And from quite the beginning, it was known that there was some connection in between. Okay. So Jones suspected it, you know, and perhaps the first precise connection came by the work of Longo. So I don't remember the date, maybe it's 87, I'm not sure I'm correct. But there is like an index that you can get for subfactors, which is kind of the index of a subgroup analogous, and that corresponds to a statistical dimension on the right-hand side. So here I say CFT, I'm extremely imprecise. I'm looking at a very particular one in the framework of Hag, Kastler, Doplischer, Hag, Roberts. Okay. And by CFT, I mean my space-time is very small. It's just the circle, you see. This is a circle. And to any region, maybe this one, let's say, you can associate an algebra of observable. And in fact, this algebra is also a von Neumann algebra, like in the left-hand side. Okay. So everything is kind of coherent spatially, and moreover, you have an action of the diffeomorphism group on it. Okay, so large group acting on it. So that's what is today a CFT. I'm not going to talk too much about that, but it's supposed to, you know, give you like a physical model of quantum field theory. So they were a link of Longo, and later they were even better. Is that for any CFT, so you take a CFT, maybe I call it A, as I did it, you can associate actually a subfactor. Okay. And that was done by Longo and Rehren, and that's 95, right? Okay. So very intriguing, very precise statement. But then Jones asks this fundamental question: does every subfactors has something to do with conformal field theory? Okay. So is there like a, so the question is, can you come back? It's kind of fundamental because it means that it will mean that any subfactor has to deal with physics in a very deep way. And moreover, the exotic object on the left will have exotic CFT on the right. So very interesting to study them. Okay. So there've been a lot of case-by-case reconstruction of subfactors. So there are a lot of factors in this program. Maybe I will say orally rather than writing because there's too many people. But I guess we can cite Longo, Kawaigashi, Feng Shu, David Evans, with a lot of people. I guess Marcel Bischoff also, he wrote like a clear paper on that. I don't know if Zhengwei has actually some reconstruction, it's quite possible as well. So many people get like some way back. There is also a beautiful article of Evans and Gannon when they try to construct some quite exotic one. Okay. And using a vertex operator algebra. Okay. Well, anyway, it's really an interesting interesting connection that many people try to dig. And Jones have been trying for many years. That was one of his fundamental questions in mind, really. He's been trying to reconstruct CFT systematically. It means that he tried to construct a machine that you give it a subfactors, whatever the subfactor is going to give you a CFT. Okay. And so the last approach, I'm not giving the details, but a last approach will start from a planar algebra, which is kind of a combinatorial object that also have a circle, but only finitely many points on it. And he tried to fill the circle by adding more and more points. Okay. So in physics, that will be called, I guess, a lattice approximation. And lattice, you can think about it like, you know, ZD approximate RD, and perhaps you can make them even smaller and smaller, changing the scale. Okay. And so he took his subfactors and tried to go in CFT, and you may almost did it, but no. He landed somewhere else. Okay. So where did he land? Well, it looks like exactly the same thing, right? You have a circle, you have like some algebra of observable. But the big difference is now that you do not act with the diffeomorphism group of the space-time S1. You act with a different group that happens to be called the Thompson's group. Okay. I guess I could put R because there are several famous Thompson's mathematicians. That's for Richard Thompson's group, or Richard. Okay. So he got some kind of discretized conformal field theory, if I may say. And so here, that was not exactly the original plan, but in fact, that was a gift that Jones made to us, because from this construction of a discrete field theory, you got a new way to construct actions of groups and to construct mathematical objects. So I'm going to talk about that a bit later. So that was the birth of what is called today Jones technology. Okay. And Jones technology gives you an explicit way to build actions of groups, typically. Okay. And so this had immediately numerous applications in various fields of mathematics, including group theory, knot theory, operator algebra, non-commutative probability. So really a plethora of nice things going out. And so what I want to talk today is a bit about here. But what I'm going to do is that I'm going to tell you what is a Thompson, and I want to submit to you, propose to you a program in that vein when the Thompson group will be replaced by a family of groups. So that's what I'm going to do. Okay. All right. So far, so good. Okay. More than 10 minutes for this slide. I could spend the whole hour on it, I think. All right. So let's go, if I can. Okay. So Richard Thompson's group. So what they are, I just talk about one group T. I need to tell you what is this object mathematically. So there are three groups that were found by Richard Thompson in the 60s, in 65, or that. So what is F? Well, it's just the group of homeomorphism of the unit interval, okay? That is piecewise linear. And when it's linear, it has a slope, a power of 2. And the breakpoint happen at dyadic rational. Okay. So any element of F, you could see it as a graph like that, okay? And so you see on each pieces, it's linear, there's a slope. Here, the slope is going to be 2, this is 1, and this is 1/2. Okay. And here you have some breakpoints. So the breakpoint is 1/2, this is 1/4. Okay, and that's 1. And you can see the data of such an element is completely cached by 2 particular partitions of 0, 1. Okay. And you say I'm taking the only affine mapping, piecewise affine mapping that puts one partition to the other. Okay. And now this specific partition, you can in fact describe them as binary trees. Okay. Just like that. So you see, you have some splitting, and each splitting corresponds to splitting your interval. So like that, for example. Right. Well, it's fine if you don't remember precisely this process, but the punchline here is that the Thompson's group is in fact described by elements of the Thompson group are described by a pair of trees. Okay. These trees, they are rooted. Okay, so remember which root we want to look at, and they have the same number of leaves. And you can only allow to have vertices that split in 2. You cannot split in 3 or 4, not for this one. Okay. So this description actually is due to Kenneth Brown in '87. Okay, and there are some larger groups. So that was F, and the T version is the same when you allow it to act on the circle. So you allow some rotation as well. Okay. And that corresponds to cyclically permuting the intervals here. Okay. And you have an even larger one that is called V. It's just traditional letter for that. When you add any permutation of the interval. So that could be piecewise, it's piecewise affine, but it can be discontinuous. Okay. Right. Nevertheless, it still acts continuously on the cantor. You can see the cantor as some kind of augmentation of 0, 1, for example. Oh. And so much later, there was another group that was given, that was independently discovered by Matt Breen and Patrick Deornois in 2006. And that is called the Brady-Thompson's group. So it's a braided version. And if I want to write an element of the Thompson's group of the braided version, it will look like that. So here it's common actually to put the tree upside down like that. Okay. But in Breen or Deornois framework, you will add a braid in between. Okay. So a group element will look like something like that. And then there is a law to compose them. Just kind of take your Thompson and you add some braid in it. So it's like a group made of both of them. Okay. So that's kind of the beast I want to look at. So this is like the approximation you would like for CFT, but in fact, what is also very interesting is that these groups are extremely precarious from group theoretical perspective. Okay, they are like groups that satisfy properties that were never witnessed before. So let's look at that. Let's look at how interesting these objects are in group theory. So the first thing is that T and V. So remember, you have this hierarchy, F inside T inside V. Well, T and V, they are actually the first example to witness the following, that they are infinite. Well, it's easy to see. They are finitely presented, and moreover, they are simple. They don't have any non-trivial normal subgroup. So it's amazing. You had to wait 65 to have such an example with this Thompson. And in fact, Thompson's groups are, until today, the primary source of simple groups with nice finiteness properties. So that's why they are so much studied. Okay. The group F was also the first example to witness the following. So it's torsion-free. Okay. It's of type F infinity. So I didn't tell you what is F infinity, but basically it means it's very finitely presented, let's say. Okay. We're going to see that a bit later. Okay. But you should think of that, it's a strength end of being finitely presented. And it's an infinite dimensional group. So what I mean by that is that if you take a classifying space of this group, necessarily it will have an arbitrary dimension of cells. So it's never going to be finite dimensional, so classifying space. Okay, you cannot. And so why I add torsion-free? Because if you are torsion, you are infinite dimensional for a stupid reason, automatically. But this group was the first one to be infinite dimensional, but without torsion. Okay. And moreover, he has remarkable finiteness properties. So that was done by Brown and Joe Higan in '84. Okay. Now, there were other properties that are a bit more operator algebraic, if I may say. I mean, and from geometric group theory. So T is not a Kashdan group. Okay, doesn't satisfy the property of Kashdan. And there is several proof of this fact. There is a proof of Reznikov, and around the same time, using a beautiful statement of Jason Ceausescu, Nawaz was able actually to prove the same thing. So if you patch together these two groups, you obtain that. And better, Farley proved in 2003, so shortly after, that actually all these groups have the Hagerup property. So you probably know that, but if you have the Hagerup property, you cannot be cache-done. Okay, so actually, Farley implies the result of before is stronger, and give you something stronger. Okay. And since then, there's been, I mean, there's been a huge amount of work on this group because they really behave strangely. And the biggest open question that you may have heard before is that knowing if F is amenable or not. Okay. And it is surprising that this question is still open, actually, that it's so difficult. Okay. But even more surprising is that a lot of weakening of amenability are still open. So nobody knows if it is Sophic. Well, you could tell me some people think that everything is Sophic, but in the meantime, it's always difficult to prove that something is Sophic. So, okay, makes sense. But it's not even known if it is weakly amenable in the sense of calling and Hagerup. And even more surprising, it's not even known if it is exact. So exact is really a strong weakening of being amenable. Okay. So this is not known. Why don't we know that? Well, all these properties that I put, almost all, you can prove them or disprove them using positive definite maps. So meaning you need some unitary representation. And today we don't have enough in our bag of representation. Apparently we don't have enough unitary representation to answer these questions. Right. Okay, so that was about the Thompson. Now, let me arrive, sorry, it's a kind of a big slide. I just want to say in 2 words what is Jones technology. Okay, so that's something that appeared published in 2017, but in fact, they were already a preprint in 14. And in fact, Jones was already talking about that in 2011. Okay, or at least the whole approximation of CFT, maybe not the Jones technology like that, that's true. But what's the idea? Well, remember the Thompson's group, as we saw it, is made of pair of trees, right? So if I come back, you see that everything is made of that. And so if you think in terms of categories, it means that a splitting is what generates your category. Okay, if you think in terms of diagrammatic category. And so a wonderful idea is that you take any category, you take any object little a in your category, take one morphism that I call it like that. Well, basically sending your forest or your tree and replacing your branching by this homomorphism will give you a functor from a category of forest. And what Jones saw is that actually give you an action of the Thompson's group. So this very mysterious and complicated group give me just one morphism wherever you want in the world of mathematics, and I give you an action of it. Almost like I will pretend this group is cyclic, if you want. It's kind of magical. And what is amazing is that actually this representation of F often, or sometimes, extends to its larger cousin, T and V. Right. So there's been a lot of application in that, and I have to say that since 2017, I've been mostly working on that, okay, on an application of this. Yeah. So for example, if I take a Hilbert space, and I take just one single isometry from H to its double tensor, I get a representation of V. Here I put representation, I mean a unitary representation. So I was saying before, we don't have any unitary representation to answer all these big questions. Here it is. Now I give like this amazing recipe to reconstruct them, okay? Now, if you change the tensor product into direct sum, it's even easier. You can also build some unitary representation, and they will extend to the larger group V. So that's really amazing. So by the way, this thing with tensor products, with Jones, we're able to give new proofs of what did Reznikov, Sergescu, Navas, and Farley right here. So we got new proof of this fact, actually. Okay. So that's quite nice. If you do direct sum, actually, the game is very different. Okay, so here you can actually build a beautiful sister algebra from it that is over the Kunz algebra. And with this method, you get like new way to build the representation of the Kunz algebra, by the way. Okay. So that was a joint work with Jones. But this joint work, I should say, like this theorem I just cited about constructing representation of Kunz algebra, that was explained to us basically by Anna Marie from Vanderbilt, I don't remember her last name, and Rui Excel within Florianopolis. And Christine Courtney did like a nice article where she actually showed that the sister algebra coming from that has exceptional properties in sister algebras. Okay. It has a lifting property, if you know what it means. Okay. And we have some work in progress with Dilshan Vijayasena, where we build a plethora of representation here, okay, that are irreducible, which is kind of rare. Okay. All right, so there's tons of other work in this direction. There's been a lot of interaction actually with skein relation, and looking at fusion category, planar algebra. That was the initial work of Jones, but there have been also some group series doing that. So Gilly Golan, Sapir, Yongsheng Ren also did in that direction, and others. Okay, I'm not going to cite everything. And there are other nice application you can get in group theory. You can do also some operator algebra, some physical model. You get like some links invariant, new links invariants. This is really an exciting direction also. And even some non-commutative probability theory. Okay, so just to give you a brief account of some directions that came from this Jones technology to show you how rich it is in terms of subjects. Okay. All right. So I could spend the whole talk to give you application, but today I'm going to do something else because I want to present you a new program that will strengthen all these directions. Okay. And the bonus is that you're going to construct some beautiful groups out of it. Okay. So let's look at that. Okay. So that's the series that I name forest categories. Actually, I was talking with Matt Zaremski, who very judiciously told me that was probably not the best name. So I may change it, but we're going to see that. I think it really makes sense, actually. I may add a skein in the title or something like that. So what is a forest category? Oh. And you should think that this definition is halfway between the world of Thompson's group and the world of Jones subfactors. Okay, tensor categories. That's really the idea. So what do you do is that I should probably draw here. That will be much easier. But anyway, I'm looking at rooted forest. Okay, going from bottom to top. So what does that even mean? This is like I should have space. Okay, so it means that they will look like that. Okay, so that's a forest. Okay, so go from bottom to top. But now the novelty is that the vertices, they may be colored by different colors. Okay, so here I put one like that, here I put one like that. Okay, so I color them. I do not color the leaves, but I color these interior vertices if you want. Okay. Now the composition is just concatenate. Okay, so if I have a forest on top, I may add that if I wish. And they will have also some prescribed colors. Everything is colored, right? Now, this will give you a category, okay? But this category will not have the properties that I want, which is like I want to construct groupoids from it. So I want to be able to invert vertices. I want to be able to invert my forests. And to do that, the key idea is to put that trees I'm going to look at prescribed trees, and I'm going to declare they are the same. Okay, so I'm going to put an equivalence relation. So if I put one example of equivalence relation will be something like that. So if I have two colors, I could declare, well, these two things are the same. Okay, exactly like what you have in planar algebras or in tensor categories. Okay, and each time I see this diagram, you see this guy, for example, this guy, sorry. Well, I may replace it. So, for example, on the left-hand side, I could just replace it. Okay, that will give me a new tree, right? So, it gives me like a quotiented forest category, and that, as I was saying, it's really mimicking skein relation. Okay, that you have in planar algebras. And so from there, if I put enough relation, so the more you put colors, the more relation you want to put, okay, in order to be able to invert morphism. While using a whole theorem of R that has more than 90 years, if your category is left cancellative, and if they are common right multiples, well, you can invert. Okay, so you get a groupoid. Okay, so any elements can be written in that way. Okay, I call it forest groupoid or fraction groupoid. Okay, that's the fraction groupoid of your category. And instead of looking at just forests, you just look at trees, you get actually a group. Okay, so if you invert trees, you get a group. Okay. And that's the groups I want to study. Okay, to see what do we get. Is it like a nice theory? Is it rich in terms of group theory? Oh. Just one remark is that this actually this structure of collection of forests has very nice property. It's actually a monoidal category. Okay. And the tensor product is just juxtaposition or concatenation horizontally of two forests. Okay, that's how it works. And moreover, everything that I'm saying, you could add some breads if you want, like I showed you before with the Brady Thompson's group, or some permutation or something like that. Everything works straight away. Okay, there's no subtlety. And moreover, everything is very functorial. Okay. So if you want to see it from a perspective of category theory or permutation theory, you can go, there's no problem. All right. Examples. Okay, I guess we need that, yeah. So which example I can give you? Well, let's take like the skein relation I gave you before. So first, what is the Thompson's groups? Well, we already saw it before. So any element of the Thompson's group, things will look like that. Okay, so that will be a pair of trees, and perhaps I'm gonna. So that would be an element. Okay, so you need to have the same number of leaves. And so the way you build it is that you have one color and you have no relation. So there is no skein relation here. Okay. Okay, fair enough. Now I'm going to do something a bit more in the spirit. I mean, a bit more deep. As a generalization is that I'm going to put two colors. Okay. And the unique relation that I'm going to put is this one. It's the same that I did before. So you're going to declare that this is the same than that. Okay. Well, this gives you in a category when you can invert everything. And actually, it's called, it's isomorphic. It gives you a group that is isomorphic at what is called the Cleary irrational slope Thompson's group. So that was defined by Cleary about 15 years ago, I believe. And recently has been quite studied actually by a group of group theories, Burillo, Nusinkis, and Reeves, where they did actually quite a lot on that. It actually inspired me for the right setup of this. But of course, you can generalize completely this kind of example. So if I take the same, then here, you see, if I put like a red, I put purple, and then my relation is something like that. So I put as much as I want. Okay, and same colors than before. Oop. That also give you a nice category, and you still have a group. Okay, out of it here. So this is still okay. We have a group. And in fact, you can show that all these groups are pairwise non-isomorphic, by the way. So I already have one parameter group. But in fact, there is tons of others. There are many others. And so what's the, okay, yeah, maybe I stop here. So that was just a few examples. I hope it's a little bit clear what we are doing. Let me just give you key aspects of this program. So one thing that is important to see is that unlike planar algebra or classical tensor categories, there are no linear structure. Okay, so all the skein relations are like two given elements. Okay. So for example, Yang-Baxter skein relation that Zheng has studied quite a lot actually in his PhD, it will be, everything will be very linear. And in fact, any skein relation in planar algebra will be like that. Like if you look at, I don't know, like the D2N that are quite easy to do, the Rha group, extended L group, etc., the fish, they all have, you have like a sum with coefficients for your skein relation. So you will have a diagram here that will be equivalent to a sum of diagram with some coefficient. Okay, so here, no coefficient, okay, and no sums. Okay, so nothing is linear here. Okay, so it's kind of a much more discrete world in some sense. Okay. Now, if you deal with tensor categories, you can give a skein relation and try to see what kind of categories you get. But what is always very hard is to check consistency, right? I think nobody will pretend the contrary. That's always a difficult question. Okay, to see if actually that makes sense is if not everything will, if you will not get everything that collapse, right? Here in this discrete series, it's much easier. And in fact, by consistency, I will say the category can give you a group. So I'm able to invert things. Okay, so that's what I would call consistency. And here we are really fortunate because Patrick Deornois spent many years giving to everybody, to the community, beautiful criteria, powerful criteria to tell you if they are consistency or not. And this particular category that I'm looking at, they are very well adapted for using Deornois. Okay, so here that's what I'm doing. I'm using Deornois techniques all the time. And they are very useful for checking one thing. They are very useful to check, yeah, it's here, to check left cancellativity, okay? Which is never that easy to do. I mean, for any example, you need to find, the right proof here. So this will give me left cancellativity for many examples for free, okay? And see, then I still need to check common right multiple, okay, which is not easy also, but depends on the example, okay. Oop. Okay, so third thing that is, well, that's one of the main motivation, of course, is that these groups, so the groups that are made from these categories, they are tailor-made for using Jones technology. It means that I can easily build functors from these categories, and these functors, they will give me unitary representation of my group or action on compact space, whatever. I will have tons of actions. And moreover, the technology of Jones is extremely nice because everything is very constructive. And if you know Jones, you know that that was always something he cared about, is that you want something effective. You can see, you can touch your example. And that's exactly what his technology is doing for us. Okay, so that's really nice for that. Oh. And now going back to the first slide. So this is like completely speculating today, because so far there is nothing precise that is proven, is that would give you more sophisticated groups or objects for approximating CFT with subfactors. Okay, so the very naive idea is that I would take, like, I don't know, like the Hagerup subfactor and try to mimic the skein relation of it, get a forest group, and see that if I can make some kind of closer discrete CFT, you know, using this skein theory in this skeleton of the category of Hagerup. Okay, so that's kind of the idea. And then moreover, I found beautiful this last application we had with the Pythagorean sister algebra. That was this sister algebra that we use in various parts of operator algebra. And here there is something that is, there will be like some new method for constructing representation of sister algebras. Okay, that usually you always need some infinite dimensional data. But here there is something that will, you would just take like some finite dimensional matrices and you will get representation of like complicated sister algebras. Okay. Okay. So that, I think that's a very powerful technique that we just really, we're really at the very beginning of that. I think it's going to be very useful. I mean, already new techniques for having like representation of Kunz algebra. I think it's really nice. Yeah. Okay. So that was about the whole framework, about this kind of, you can see it's really a program in the vein of Jones, where if I come back at the beginning, this Thompson's group, I will just put like a forest group, okay, made of a certain category. And this category F of forest will be, you know, coming from my subfactors, from the categories that I have for a specific subfactors. Okay, so that's kind of the idea. Okay, but now what I'm going to do is that I'm going to forget this slide, and I'm just going to focus on particular property of a forest group. Okay, that's what I'm going to do. So I will forget this big picture and see what we get. So first, how do they look like, all these groups? Okay, that I constructed with this diagram of forest that I model out by some diagrammatic relation. Well, they all contain a copy of F. Okay, so remember, this is kind of the hierarchy, and I guess I have that with BV when I remove the break. So they are all infinite. Okay, they are not elementary amenable, so of course I cannot tell you if they are amenable or not, at least in general, I mean, because they contain F. They have exponential growth, so they have big balls, and they have infinite geometric dimension. All of these statements are kind of trivial if you know that they contain F and if you know a bit about what is F. Now, what is non-trivial is actually they are finitely generated or presented when there is, if you want, finitely many colors. And then for the respectively is like when there is finitely many colors and finitely many skein relation. Okay, that assures that it's not, it is not if and only if, but there is one direction. Moreover, I can give you explicit presentation of any of these groups. How can I do that? Because I know an explicit classifying space. Okay. Maybe I call it BG. That's the classical one. So I can give you a BG that comes from a simply shell complex, actually. So it's a kind of a nice structure. Moreover, there is something. So all these Thompson's group, as you have seen, they typically act on by piecewise linear, piecewise affine maps. Okay. Well, here I don't have that. Too bad. But actually, they act on a totally ordered set. And what is nice is that this totally ordered set, I can construct it canonically from my forest category. Okay, so I do it actually using Jones technology. But what is amazing is that this Jones technology works whichever is the skein relation of your forest. So it's really canonical. Okay. And this actually action, there are some consequences of the existence of that. Okay, maybe I talk about it after. So unlike F, they may have torsion. They may have finite conjugacy classes. So meaning that they may not give you a 2-1 factor if you look at the group from the algebra, not all the time. And they may even have a center. Okay, very different from F. They may contain a copy of the free group. So at least some of them are not amenable. Okay, so they are not exactly like F, right? You see. Some of them can surject onto F, and in fact, you can give you a split exact sequence, it give you like a semi-direct product. And some of them do not surject, and they may even have their derived group that is simple. Okay. So this is probably a very exciting direction to go to. That's one of the most logical one if you're a group theorist. I have not investigated too much on that, but I think it's a very interesting direction to look at. Yeah. So actually, one of my students, Ryan Selig, is looking at that right now. Yeah, I think it's a very beautiful question. Okay, so that was properties of groups. Yeah. All right, so you know, I tell you, well, you can do all these things, but I gave you some examples. But now I'm going to give you like a recipe that gives you so many examples. And I was very surprised to find this recipe, okay? Because I did many particular cases, and then one morning I was like, oh, but actually, there's this proof that works. It's much easier to do, and it works with a huge amount of generality. Okay, so let's look what it is. So I consider two trees that are monochromatic, okay? It means that they are in one color. So let's say, maybe I do them in black. So whichever tree you prefer, they just need to have the same number of leaves. So maybe I could take this one, okay? So that's my T, that's my S. Now I color all the vertices of T in red, okay? And the other in blue. Let's do that. Okay. And now I define these forest categories. 2 colors, 1 relation. Okay. And now the miracle arrives. It is consistent in the sense I gave you, I tell you. So it means it's left cancellative. This I have it for free, thanks to Patrick de Hornoy. And moreover, it satisfies that there are some common multiple, common right multiples. And this is easy to prove. Why? Because, well, because your trees are monochromatic. Okay, so now you see, I didn't mix up the colors. It's only all red or all blue for TNS, you see. And because of that, the miracle happened. If I had mixed it, the colors, that will be case by case. And trust me, it will not be easy, and it will be surprising the answer you get. Okay. All right, so you get a group. Okay, nice. Is it an interesting group to look at? Well, it is. So it's of type F infinity. So what does that even mean? It means that for any n, you can find a classifying space of this group such that it has finite n skeleton. It means that up to n, up to dimension n, there are finitely many cells. Okay. And so if you do it for n is equal to 1, it means you are finitely generated. If you do it for n is equal to 2, it means you are finitely presented. And then you can do it for n equals 3, 4, 5. So here I'm telling you, it's true for any n, for any of these groups. Okay, so it's a huge source of group with this property. And you may get that there are not so many groups satisfying F infinity. Okay. Now, not only it's true for the T version, the F version like that, but I may also add some braid or some permutation on top. It's completely fine. And they're still of type F infinity. Okay. So even the braided version, it's going to be like that. Okay. And here I do it for 2 colors and 2 trees. In fact, you can take any number of trees and do the same construction, even infinitely many if you want. If you take finitely many, you will still have a group of type F infinity. If you take too many, it will stop being an F infinity, but you can still have a group, meaning that it's still consistent, the relation. Okay. It means also that you can do some direct limits, some projective limits, etc. So you can also leave the world of discrete group if you wish, okay, by doing some projective limits, for example. How do I prove type F infinity? Well, here I was quite lucky because I could use a different theory that was done by Thumann, and that was in 2017. He did his PhD. So the article is 17, so PhD is right before. And Thumann, he did like a brilliant PhD, okay? That come after a lot of theorem in this topic, okay? So that basically it come after Brown in 87, Brown, Joe Higan that I already cited, and a lot of people like when I was saying Zaremski, Witzel, Nusinkis, or there are so many people I cannot cite all of them. And so they managed to have like more and more techniques. Farley also, who did a big thing, Hugh. Okay, I cannot cite everybody, but a lot of people in group theory doing more than 30, during 35 years, give you like tons of theorem and new techniques to prove that groups that looks like Thompson are of type F infinity. And Thumann managed to do a synthesis of them using category theory and to englobe in one single framework a lot of this accomplishment, okay? Okay, a lot of them. And I could extract from his theory what I needed to prove that all my groups are of type F infinity, okay? All these groups at least. Okay. So that's what I did. Okay. So at the end of the day, what do you get? Well, you get that from very minimal data, so 2 binary trees, you are able to construct one group, and this group happens to be interesting. And now there's a lot to do because you would like to know how other properties it has. So as I was saying, Thompson's groups are the main source for infinite simple groups with nice finiteness property. Here you have infinite, you have nice finiteness properties. Can you take from them simple subgroups or something like that? Okay. Do you have like the T and V or B or T or V version are simple? Do you have like derived subgroup? Do you have like finite index simple subgroups? I don't know today, but I'm sure there are a lot. Okay. All right. So that was like for the application of the group part, and I think I already talked quite a lot. So I just stop here and thank you for your attention.
Thank you, Arnaud, for this very beautiful talk. So if you have any question, please unmute yourself and ask.
First question, do you know anything about the group forming algebra of the new groups?
So yeah, it's a great question. So I haven't looked so much, but what I know is that in January there was an article of Zaremski, one of his students called Eli. I don't remember his last name, and they look at groups similar to this one. They build them using another technology called cloning system of groups. And if you want, instead of having your skein theory inside, it's more on the leaves. So here you will have some group elements, you see, on your leaves. And when you grow your tree, you need to have rules about how you change your system. And they look at group fundamental algebra and they could get a lot of MacDuff 1, okay? So central sequences, etc. And yeah, that was one thing. One thing I can tell you is that I did a similar construction before. And when you decorate the leaves, so not the skein theory, with a group that has a high group property, Well, the larger group will also have high group. And so does the group for the algebra, right? But I do not know too much. Sometimes you get some risk products, so you could expect maybe you can do some rigidity result about that, but I really didn't look too much about that. Yeah. You know, I got a bit I'm annoyed by this fundamental algebra because they forget all the information. You give them a group and they forget if it is amenable, they forget everything. So I've been more classifying the groups themselves this time. But yeah, I'm curious about properties that resist to fundamental algebra. So I'd like to get like some Kazhdan property somewhere. You see, for example, I already have some high group. I don't know if they are hyperfinite since I don't know if they are amenable. Some of them are not, but I do not know if they give you infinitely many fundamental algebra, for example. This I don't know. Perhaps yes, perhaps not. Yeah. Many of them will give you 2-1 factors. You will get some ICC1, but not all of them. That's true. Yeah.
So I have a question also.
Mm-hmm.
So from a subfactor, you can produce a forest category and a forest group. There is no choice, I guess.
Well, I don't know. So yeah, so I will start with my subfactors. That's true. Then I could look at let's say the tensor category. So let's say I take like the planar algebra. Let's pretend it's unshaded. So, and perhaps I'm able to find a nice skein theory with one generator, for example, like the like the high group, like would be like sometimes it's 6 or sometimes it's 8. And from there, I'd like to extract the skein theory and do it like without coefficients. So there's not so far a clear recipe how I go from there to a forest category.
So this
right
may
now, I
depend.
don't know.
This may depend on the choice of the presentation, the choice of the skein theory. I mean.
That's right. Yeah, yeah, that's also right. Yeah, yeah.
And so, which subfactor produce the Thompson group, in fact?
So the Thompson, at the beginning, Jones, he will take Thompson for any subfactor.
Ah.
You see? And the idea of this like program in the vein of the one of Jones is to be a bit more precise, a bit more pay more attention of which groups you're going to construct. And that's why I put this theory of forest categories, because then you are allowed to take like a category that looks like a bit more the category that gives you a subfactor. Okay. But why I do that, there is one comment that Jones made a while ago. That was, I don't know, well, I was still in Vanderbilt, so I guess it was 2015 or 16. He was saying, so he was developing this technology, and the technology was basically you take this forest, for example, this one, and now you go in a planar algebra and you put some R. You know that Jones always like to put this R, right, for transform matrix or something like that. Or perhaps I had a leg here to be sure I have a subfactor planar algebra. And maybe I put more legs, but let's pretend it's like that. You say, what happens if R generates high group, the high group subfactor? Don't always say the representation you will get from Thompson should carry interesting information. So that's a very vague statement. And I would say my program is a bit with this kind of vague idea that you could approximate in some sense. Okay. That's kind of, yeah, the idea of that. Yeah.
Mm-hmm.
So it's very imprecise today. Yeah.
So from any subfactor, you can Jones produce a Thompson group, but in your program, you can do something more, something finer. You you produce another group. So
Exactly,
why
that's
you,
the idea.
yeah. So what is the
so,
difference?
So,
Why
yeah,
one
so
way
now
you, yeah.
Let's see. Yeah, so any subfactor, you had always the same group T, that is Thompson, that act on some kind of discrete CFT. Okay. So that was one thing. Then second, that also give you unitary rep of T. Okay.
Mm-hmm.
Now what I do is that I take that, but in fact, instead of having T, the Thompson's group, I have a group that is acting also on something, on some discrete CFT. But now F kind of remembers in some sense the category of N inside M, or is built from the category of NM. Mm. While here on the top, you just take always the same group. Okay. This group was obtained by doing some refinement on lattices, and this refinement would be like if you have a point, you can make 3 points by just putting a R in between. And here, this refinement, I will do it, but with various R. Okay, each color will give me a different R. So that's the idea. Okay. So you get like a different inductive limit to construct a discrete CFT. And moreover, now you have family of groups instead of one group. And you can also do the same. You can build action of them. So you can also study them as group. Okay. And who knows if subfactors IDs give you also interesting groups, you see, to study with different mathematical techniques.
Mm-hmm. Okay. And did you try to make explicit computation from the a group or extended a group subfactor? Do you have an explicit group? Yeah.
Not yet actually. I've been so distracted by learning new group theory that I've been doing a lot of that. Yeah. So I've been like looking at tons of forest groups. I've been trying to understand what they are. Are they all the same? Do they have like some of the exceptional properties of Thompson's groups? Can I say anything new in group theory? And so in fact, all these questions, the answer is yes. So I was very happy about that because I didn't go with any expectation. You know, I just explore and look. And it turns out there are a lot of nice things to discover. And now I really want also I want to dig the Jones technology. I want to build some nice system algebra out of it. I want to look at what kind of representation you get. Yeah. There's so many things to do that you have kind of, you need to choose one direction. Yeah. So far it has been that, yeah.
Okay. So is there another question? Other question. So, yeah. So you talk about Jones technology, Jones' new technology about Thompson group. But there is also the Jones technology about planar algebra. So you did not talk too much about planar algebra.
Yeah, it's just a name that I gave to that actually, like this new way to build the action of groups.
So these two technologies are really different. They are
absolutely.
Made, yeah.
Absolutely, but in fact, you can put them together in some sense. So I can show you very easily what's going on. So you take C, a category, whatever it is. And if you are lucky, you can construct frac F that is a group. Okay, so that's from the studies. Now, what say Jones? He say, well, let's say if I go from C to Hilb, and that's a new thing of Jones, then I can find there exists pi that give me, I can construct pi that goes from this group that I build from my, sorry, so C, from my the group of my category to Hilb. And in fact, it just gives me a unitary representation on a Hilbert space. Okay. So that's what is new of Jones. That's what I call the Jones technology. And now, why do I say it's linked? Because perhaps instead of going to a Hilbert space, I go into a planar algebra, let's say. Okay. So one planar algebra. It's a tensor category. And Jones will tell you that you have also a unitary representation. So I take a planar algebra, so I know I have an inner product, etc., and I can do that. And so for Thompson, what it is? For Thompson, what it is, where you just have one morphism in your category, and you send that to one morphism like that belongs to a planar algebra. Okay. And so this gives a unitary rep of F of Thompson. Okay. And that was the very first thing that Vaughan Jones did, actually. Okay. That's the first instance of this new Jones technology is that he took a planar algebra, he chose one object, one element like that, okay? Like here it's a 2 box. And to that, he could build an action of the Thompson's group. So if you go in temporary lib Jones, what can you put? You can put something like that. So you put a coefficient here, plus beta. What you need to ask is that the right-hand side is an isometry in your planar algebra. It means that if you put it upside down and look, your inner product should give you 1. Okay. Or you should have like the entity, the identity. And yeah, this gives you a unitary rep of F. And actually, this precise representation, we study them with Valeriano Aiello and Roberto Conti when I was in Rome, actually. That's my unique collaboration where we only talk in Italian during a year. So I learned as much Italian than mathematics by doing this project, essentially. But yeah, so they are really interesting representation. Yeah. But we couldn't classify them. We could only show there were 3 different for this 2 parameter family. Yeah.
Okay. Any other question? Shangwei, you have nothing else to say? No? Okay, then thank you, Arnaud, again for your very nice talk.
No problem.
And I hope to see you soon.
Yeah, I'll try to come. I'd like to actually, yeah. It would be easier, absolutely. How does it work for the? So you recorded it.